Yeah. Good afternoon, everyone. I hope you can hear me now. So I will try to talk a little bit deeper on the hazard mitigation. So a few words about me. I'm the power system consultant. I generally model the electrical system. A big part of my work is arc flash risk assessments. And I do it from 14, 15 years almost. 1 year in wind turbine design. So we have something in common with Jenny. And so let's go further. I will try to show you today what's the agenda. So I will briefly talk about the mitigation equipment overview. Jenny did it very well, so I will just go very briefly about it. We talk about the most common solutions, and I will try to show some examples and videos. Examples from real system from calculation, so difference what it makes. And I encourage all of you to ask questions. So if you have any question now, ask it now in the Q&A or chat. And if you have something more complicated, my contacts are there, you should have it, and feel free to ask me. I'm always open, I always try to help. So let's go. So arc flash mitigation overview. Coming back to NFP 70, we have a hierarchy of controls, very nice actually table. This may look like this. So you can actually see what is most effective, what is less effective. Today we are looking on the, so I'll be trying to tell you a little bit more about elimination, substitution, which is reduction and changing things, so accuracy and switch gears, and engineering controls, a bit on hardware, let's say, side. So Jenny already explained you very well about it. I will just briefly show you because this will be referenced later. So of course we have OC overcurrent settings improvements. That's how we can reduce the energy. Active fiber optic detection, maybe current limiting fuse. In medium voltage, you may see ES limiters name, maintenance mode or arc flash reduction maintenance, which depend on the manufacturer. So this is for the low voltage breakers. Zone selective interlocks, if you have communications, differential protection. And when we talk about the reduction, we talk about lowering the energy somewhere between 1.2 to 12 calories. So it's not fully elimination, it's more reduction. And we can also reduce the likelihood, so we can have proper covers in our panels. We can have better forms of separation. So when we design or when we order our panel, we can ask for higher separation forms, if that's possible. We can have internal arc class for medium voltage switchgears and arc resistant or in the internal arc classification for low voltage panels. This is very nice to have, but this is something when you build a new system. And of course, lockout tagout. So that's how we, let's say, reduce the overall risk. There is also short circuit current adjustment. And this is a very specific topic, which sometimes helps, sometimes not. So that's, let's say, project specific topic. And the same, we can move people further away. So what Jenny saw, chicken switch, infrared windows, remote racking, motor operated breakers, and everything which is SCADA or remote operation is very welcome things. Because if we are not there, problem stays, but we are not there. So it's not our problem at this point. So we move people further away. And some brief explanation behind it. So of course, we can design the switchgears as an internal arc classified, which is a very nice thing to have. Important thing to remember, there are some requirements associated with it. So if you have low voltage or medium voltage switchgear like this, or usually you need to have it closed, locked, sealed for this thing to, let's say, be in operation. If you open the doors and you try to do something, you don't have this anymore most of the time. And just an example for it. That's the test that was okay. So we try to keep it short. And the same one is, which was fail. Well, I don't think I have to explain a lot about it, so we can actually see it. Those videos are longer, but just because of the limited time we have now, I try to keep it short. I mentioned something about the switchgear covers. And so generally it means the IP level of the panel, but also the covers. So we can have IP2X covers inside the panels. Those are photos from the real sites when I'm visiting. So if you can see on the left side, there is no cover. And you can see here, cable connection, bus bar. This is kind of dangerous from shock hazard point of view, one thing. And also it's much easier to create the arc flash now here, which is the other, let's say, second effect. On the right side, it doesn't maybe look good, but generally everything is covered now. So it's not that easy to accidentally touch something, which also makes it much better from arc flash point of view. So we can also talk about the form of separation very briefly again, just to show you. Form of separation is just the form how we build the panels and how much separation they have between each compartment, and from nothing to everything. And this is an example again from the side. So I open one big door to see something like this. And this is not a good thing because you can see straight through the panel, grab the bus bar, generally dangerous thing. If you have 1 to 6 risk ratio, this will be 6. And the same thing was the same side. That was form 3B or 4B. I don't know because I didn't have to open it even. So that was reducing the risk. I was going for settings. I can see it, I can read it, that's done. But if you would like to go to, let's say, operation compartment, whatever is inside this compartment from control side, you can open this one. And because it's fully, let's say, separated, it doesn't increase the risk. So you don't have really necessary PPE for doing this thing. But if you try to open this and this, of course, you need to have something. So most common solutions. So what I did for today, I prepared some, actually I cut out example from one of the project. Not everyone is technical, so I'll just maybe briefly explain it. This is the model from the software, precisely from SKM. And, this small thing is a medium voltage switchgear. This is a transformer, and this is a low voltage switchgear. And we have somewhere downstream small distribution panel. And I will use this to show you the difference between each systems. And what I focus today, and that's what we most common will see in the field, overcurrent settings improvements. So that's the most common. I would say 95% things that we do. Maintenance mode functions that are implemented in mini or low voltage breakers. That's the second thing. And the arc flash detection system that Jenny explained before is not the last one, but the most common thing. So, small question to all of us. Where do you expect to see highest incident energy? Not the risk, but the highest incident energy. So you should see the pool. I will give you a few seconds to answer. 1, 2, 3, 4, 5, and we are done. Low voltage switchgear. Yeah, and the mini voltage switchgear. I will show you an example answer now. So the low voltage switchgear is correct. The only thing is that we actually talk about the line side of a low voltage switchgear. That's what typically happens. Medium voltage was a good shot, but usually in most cases, medium voltage is not that big issue. Apparently, that's just it's not because I don't want to have it, just because that's how it works most projects. And so what you see now is the existing situation. That's a base that I will use to show you the difference how we go through each system. So this is our base as a reference, and I will make some modification to settings, to maintenance mode, and the arc flash detection system, and I will show you how it improves or not. So just small explanation here. So you can see 19.9 calories, especially I use the colors like in the projects now, just to show it so it's more visible. And that's a lot. And this is on the line side of low voltage switchgear. And I will explain it in a minute. Switchgear itself is 20 calories and medium voltage size 18. And this area is actually not really for us today because we are not evaluating. We're not going to change anything because we don't know upstream information. And this is a TCC, which is time current curves, graphical presentation of overcurrent settings. So it's not exactly perfect, but it's not even exactly bad. So I mentioned something like the line, bus side, and so on. So just a reminder, I'll explain it. So every panel has something like line and bus side. Line side is a supply side, incoming side, which means here are connected the cables from transformer in this case. And this area is protected by, let's say, in this case, it was a medium voltage relay upstream in the system. And then we have a main breaker, and upstream the breaker, we have a bus side, which is everything protected by this breaker. This is important to know because there is a big difference between those two. That's the difference that we saw 19 versus 20 calories. So usually this is the area with the highest problem most of the time. So we go to overcurrent settings, and I need to give you some short introduction to it before we jump into real example. So when we talk about the overcurrent settings, we would like to modify the settings, in this case on the low voltage breaker. So I make this example to show you the influence on the short circuit current on arc flash. Just briefly, as you can see, the lower the current, the higher the energy goes, and that's because it's not maybe intuitive, but generally it's because we're increasing the time, and this is very visible when you have a low voltage breaker. So when we start for 37 kiloamps and very fast tripping, 60 milliseconds, we have 8 calories. And if we go down through the system, and because of the changing tripping time, we end up somewhere at, let's say, 0.5, which was 2 kiloamps, which is on the border on the arc flash, and 20 seconds, 130 calories. That's because of the very, very, very long time. We don't want to have something like this, but this is generally how these things behave. There is one thing why we evaluate the settings so much. That's because sometimes the settings are on the edge. So they are very close to the arc flash current, and sometimes it's too close. And we also take into account some variation of the arc flash current as a double check. And you may see that sometimes there is big difference between tripping time. It can go from 120 milliseconds like here to 2 seconds. So that's a huge jump, and also a huge jump in energy from 3 calories to 42. So we would like to have some, let's say, space, so we accommodate for this variation. And for some people that are maybe more used to or see more fuses in the systems, with fuses is more logical. So the bigger the fuse, the worse it is. In the same system, if we just keep exchanging the fuse in the same place, it will get worse and worse. And the same, if the current goes lower, it will be generally worse. There was one word that I have to maybe add, it's not on the slide. There are some current limiting fuse, which can be utilized as also arc flash mitigation technique. If you add it properly to the system, they will reduce the current, and they also will dramatically reduce the instant energy. But that has to be done in the proper way. So let's go to the real example. So I made some changes to the settings, improve it. We also have to keep it selective, which means that they have to operate in a certain sequence. And with this, so we didn't really, I actually improve it from selectivity point of view, and I improve it from arc flash point of view. And you can see that our energy is going down now. So nothing changed here on the distribution level, but on the main bus bar, we go to 7 calories from 20, and from 90 to 19, which is a big difference. And of course, we improve a little bit the 10 kV side here. And this is just for properly adjusting the protective settings for our specific electrical system. So what else we can do? We can implement arc flash maintenance mode, or maintenance mode, doesn't matter how it's called. The idea behind it is like in this example for low voltage breakers. Usually this is a separate function built in trip unit. So we need to have a specific trip unit in your low voltage breaker. I used to work in Eaton, that's why I have a lot of Eaton examples. And if you can see here, that used to be, there's a trip unit. Here we have special knob, which is to activate, deactivate the maintenance mode. And that's the idea behind it is that trip unit will temporarily override the settings to make it much faster. We also have to check it if this will make actually better, because sometimes the current is too low that will not even grab it. But in, let's say, 99% of cases, it will work. So in this example, we temporarily go down from 10 calories to 2.2. And that's the way how it works is just because we would like to have it for a short period of time, for maintenance time. We go somewhere for 1-2 hours. Safety is more important than selectivity because we are doing something. If something happens, eventually it doesn't matter. So we try to increase the safety here. And the same thing we can do on the medium voltage relay, a slightly different way, because we can reprogram the relay with the second group of settings, can be adaptive or can be activated by the switch, which switches outside, maybe, I don't know, somewhere else, or on the panel usually. with lockout tagout functionality, so no one will change it. And I think Jenny mentioned it about it, that it's very important to revert it. So it has to be incorporated in the procedure, that we don't forget about it. Sometimes it's good when you have a like trapped key, so we have to come back before you activate something and change it back. So that's the important step. Otherwise, we will compromise our selectivity, which means operation of the system. So when we use the maintenance mode, and I used here on the medium voltage and on the low voltage also, and not without the reason, because low voltage will work not for line side, will not improve the line side. That's why I also made it for the medium voltage area, because now we can improve the line side also on the low voltage side. There's a lot of wording. So you can actually see we go down, and from 7 to 2 calories on the low voltage panel, low voltage switchgear, and then from line side, which was 19 before, now to 8. So that's already difference. And of course, it will compromise the selectivity, but only temporarily. And if we have this option, why not to use it? So the last thing for today was arc detection systems, and brief explanation behind it. So the arc detection system is what Jenny mentioned, and she showed you a real life example. I will show you the whole system. You have a sensor that will detect the light, specific waves of the light, and send a signal to the, let's say, main unit, which will send the signals to trip the breakers. And it depends on the system. Usually it works somewhere around 4 to 5 milliseconds as a detection time and sending the signals. And then we have to add to it a circuit breaker reaction time, which is something around 40, 50 milliseconds, depends on breaker. And for the medium voltage, it can be 100 milliseconds even. So we have system like this. And I'll show you an example because it's easier to explain it this way. It's a very nice video of the Schweizer lab. So 50 milliseconds versus 50 milliseconds, 500 versus 50. Slow motion always appreciated. So you can actually see the pulsing, the cycles of the wave.
Excellent video, Master. Yeah. Very, very good video.
Yeah, I think it's self-explanatory. So that's what it is, 12 calories versus 1.2. So it's a significant difference. And the very big advantage of those systems are that they are separate hardware solutions that you use in your, let's say, system, which will not affect your selectivity. So they work aside. And we can play with the selective when we reach the limits, and that's typically where I use it. If we cannot reduce energy anything lower, we cannot improve the settings because of the limitation of selectivity. Then we usually go to arc flash detection systems, and they allow us to keep the settings separately in a different way, and they work on the separate. There was one thing that I have to mention here, because maybe you don't see it, because what I did, we improved the, actually you see, we improved the line side more, to down from 8 to 3.5, and the bus itself is around 3 or what was 2 calories, and the rest more or less stays the same. Here is small difference on the medium voltage, but generally speaking, there is also communication. So our system is installed here, but in order to protect the line side, we have to send the signal, trip signal, back to the medium voltage relay or breaker to trip it, and that makes a difference here. That's the idea behind it. So usually you have to combine it as a complete system in order to make it work well. But that's the difference. That's a summary from it. You can actually see that we start from 90, we can end up around 3.5, but even 8.7 was very good already results. So that's a huge improvement. And that's possible in most of the projects, I would say. There is one thing nice, I think, to mention, because I show you the part of the system, and this system usually can be extended with the quenching device, which is a three-phase short-circuit device activated in different way. Here I have an example from Arctech when they use, I think, Thomson coil. So it can work in multiple times, and sometimes it's one-time use, depends on the system. But the idea behind it is that it will short circuit the free phase and then send the signal to all the breakers to deactivate. And the arc flash will be, let's say, extinguished in 4 or 5 milliseconds, which is very, very, very fast. And this system is the only system actually that can protect the equipment, because normally we focus on protecting people. Not because usually there is some certain damage to equipment eventually, but this thing also can protect the equipment itself. And just to give you again an example, easier to show than to explain it. So that's the system without it. As part of testing, showing. And that's the system with. So you can actually see that the arc is created the same way, but cannot, let's say, escalate. So it will be cut in half cycle. So we'll not reach the pressure, not to reach the highest temperatures, everything else. So we try to be as fast as possible in this case, and this will protect. Usually if you do inspection to your panel, and you have to disconnect, of course, because we created a three-phase short circuit now. So we have to disconnect the quenching device and maybe recharge it, make the inspection, visual inspection, and then decide if we go or not. But then we can activate the system again and energize the panel once we find out what happened, of course. So that's from my side for today, and just a brief summary for you. So usually we always start to identify the existing hazard level, which means that we don't really jump into solutions before we know what the risk is. You know, that's the first thing to do. We have to verify system-specific operation procedures. Like, for example, when it's from wind systems, so wind turbines, when you have a confined space, sometimes the switchgear is on the bottom or on the top, which means you have to sometimes focus more on mitigation than actually on PPE, because that's a more convenient and best way to do. Sometimes we have remote operation, which we can utilize. And then usually what I do, we go to settings improvements, then we go for possible hardware upgrades, like a new relay, medium maintenance mode trip units and things like this. And there's sometimes, and of course increasing the distance, so using all the remote operation things. I mentioned one thing here, maybe not, that sometimes ACTA's study is 1.1 brick too much. So customers decide to make actually hardware upgrades. And because it's so unsafe and old and everything else and not reliable, that we decide, okay, let's go for the new one and exchange it. So in most of the installation, it's relatively simple and easy to, let's say, reduce the energy. I don't remember the project when it was very bad to do it. And so usually 90%, 95%, there is always some space to improve and make it safer. We can take sometimes advantage of the system design and changing the procedure. That's what I mentioned before. And maybe what you saw at the last slide, that we went below 1.2 calories at medium voltage level at some point, which means that sometimes it's easier to go to the medium voltage to switch off the complete system if we really have to. And, you have to keep in mind, as one reminder here, that even if you have a brand new installation, it doesn't mean by rule of thumb that it's safe. It should be, but if ACFAS was not taken into part as a design process, most of the cases actually it's not. And I even skipped the situation when the whole factory is set on the default settings. But we talk more about the situation when you, like, simple comparison is like you buy a brand new car. It can be, I don't know, top quality, super extra safe car with all the systems, or the very low basic thing that will just take you from A to B, which makes a difference when you have an accident at the end. So that's from my side for today. Thank you all. And again, I encourage everyone to ask questions if you have it now or later. You should have my contact details. Thank you.
Martin, that was excellent. Thank you very, very much. And same to Jenny as well. So we're going to be moving on to the Q&A session. There's quite a lot of interesting questions that have come through. Just quickly, so I think in a couple of months, the following webinar will be coming up, where we are looking at, again, preventing electrical safety incidents within the workplace, and mainly focusing on the administrative good processing control, so safety rules, review of maintenance intervals, competency assessments, contractor assessments, creating safe working zones, safe isolations, lockout, tagout, permits to work, signage, labeling, guarding, specific training. So a lot going into the administrative side. So stay tuned, and you'll receive some kind of notification advising you the specific date. So Marcin, next slide.
Yep.
So good. I think now we're on to the live Q&A. So you can probably stop sharing. And Anthony, do you want to kick us off with the questions and answers?
Yeah, good. So long as everyone can hear me loud and clear.
Yep,
So first question then is what is the difference between flash and blast, and how anyone can calculate arc or blast? So Jenny or Martin, who wants to have a answer that one?
Well, I can answer it. It's quite simple. So when we talk about the blast, we talk about the pressure that arc flash actually causes. And when we talk about the arc flash as a conventional thing, we talk about the energy, thermal energy that we are trying to protect ourselves from. So in a practical way, it will mean that if you have a very high short circuit current in your system, like let's say 80 kiloamps, 100 kiloamps, things like this, it makes much more, let's say, density on the heat transfer, which will make very rapid pressure increase inside the compartment. And then if the system is not designed very well, or let's say if it was not prepared for it, it can very fast open the doors and hit you with it. But technically speaking, there is no recorded death from it. At least I haven't seen that arc blast was killed someone. So PP works apparently.
I think what you say there is really key, isn't it, Martin? Is that you can't calculate the blast the same, and obviously if the equipment is arc rated, it's designed to contain the energy being released, as you showed in your videos, when it's not designed in it is. But yeah, arc flash you can calculate, blast it's not so easy to calculate.
Well, you can calculate arc blast if you want. Let's say conservative way.
Yeah.
There is a equation for it, very rarely used.
Yeah.
But and then the more complicated is FMEA type of calculation. So it is possible. It's not that it's not possible. It's just more complicated.
That's good. I hope that helps. So next one then is which mitigation system is most often used? I guess that's down to each company as to what they decide to go with. Go on, Jenny.
I think Marcin covered that earlier on the fact that overcurrent settings and actually looking at your protection settings and reviewing those is one of the easiest ways of achieving arc flash mitigation without too many additional costs.
And as I had, maintenance mode is kind of part of overcurrent settings. So the second will be fiber optic detection.
That's good. Very, very good. Another one here now is chicken switch. So to encourage more people to utilize the device, is there a name which would promote people to utilize, such as manual assist switch? You've had a bit to do with this, Jenny, haven't you, in the USA? The actual brand of chicken switch?
Yeah, I think chicken switch is actually a brand. Other references are to like umbilicals or things like that, or remote switching device, things like that. So I think, as you say, chicken switch is actually a brand name. We didn't come up with it.
Yeah, I think they were one of the earlier companies to come out with a device for keeping the user at a distance, and I guess sometimes it's really cool to be a chicken rather than try and operate it in front of the actual equipment itself. So, but good point there. I hope that's answered the question. So I have brand new switchgear. There should be no problem with arc flash. Is that right?
So I kind of answered it on the end. So you have to still check it. There is no rule of thumb that something is new and it's safe.
Yeah, that's good.
Yeah, you also need to make sure that from your short circuit study that you're actually within the actual switchgear rating as well, because if you're over the rating of the switchgear, you can't guarantee it will behave in the manner in which you expect.
Yeah, well, that's crucial, isn't it? Yeah. That's good. Can't I just buy 40 cal PPE sets and skip all this? Well, I guess you can do.
Well, would be nice, but generally speaking, you saw the example, and that was real life example. We end up somewhere at 90 calories. And recently I have two sites where it was 60 and 75. So no, unfortunately not. You still have to evaluate it.
Yeah, that's correct. So I have internal arc classified, so arc fault resistant, LV switchgear. So arc flash should not be a problem for us. I guess that kind of links to the last question to a degree. It's my second to last question.
Yeah, I can. Or Jenny, if you want.
Carry on, as I say.
Okay. So generally speaking, it should be okay for normal operation. So if you don't do anything else around it, but if this is, for example, low voltage panel and you try to do some maintenance, live maintenance or switching off, proving that, then you have to open things and then you don't have it anymore.
Yeah.
So it's partially true.
Yeah, it's when the panels are open, isn't it? That's when you risk then, or the safety disappears. So can Jenny advise from her experience the highest risk areas for arc flash in the wind turbine?
In my view, it's very similar to when Marsan did his study. It's just before the LV switchgear. So you've particularly where you've got turbines that have the transformer in the nacelle. You've got buzz bars that go from the low side of the transformer to the through the cabinet to the first LV switchgear. And the problem is with that area is the protection that covers that zone is effectively the fuses normally on the high side of the transformer, or protection on the high side of the transformer. So because you've got a very high impedance of the transformer, it's very difficult to detect a fault on those buzz bars. And that was the picture I showed in my presentation, where they'd been wrapped in insulation to reduce the probability of a fault. But that to me is where the worst case is within a turbine.
That's really good. Thanks, Jenny. So HV governance, is there industry standards available to share?
Depends what you mean, because we build things in a certain way and all standards are available. So I don't really know what to answer here.
I think also,
yeah, it is available to share.
I think also it depends what industry. And so Jenny, from within the wind sector, many different sectors would have their own, each business would have its own set of governance, but also there'd be, typically speaking, commonly used governance, wouldn't there, Jenny, across a series of different industries?
Yeah, there's some of the standards are like the NFPA 70E is a quite common standard that's used. The IEEE, Marsan could probably tell me which one it is, because I keep getting them confused. Is it 1584, I think? It gives you calculations. So there are arc flash standards out there. Most of them have come from the US because they are slightly more ahead of everyone else in terms of standards for this type of thing.
Yeah, that's good. And I guess also another one is CSA Z462 as well as another very, very useful tool. So another one is, I'm aware how to remotely operate an ACB. Can you retrofit to remotely operate an MCCB?
Sometimes. Things are changing very fast. So in past it was not possible, now it is. Even they have zone selective interlock and measurements, everything else. So in the very brand new, it should be possible.
Yeah, if there's a way of getting a signal to it to cause it to trip, then you can operate it remotely. Well, you can get it to trip remotely. Whether you can close it remotely, it would also obviously need a signal for that. But if you can get external wiring to it, then it should be possible.
Hope that helps. So at what voltage can arc flash occur?
Well, officially 1208 volts and above for AC, and let's say 50 DC and up. When we talk about the dangerous arc flash,
Yeah.
just above 1.2, because testing was done, IEEE 1584 done extensive testing for 2018 revision, and something like 48 volt DC, very big batteries. It can also have some significant energy. But in practice, we go down in Europe, let's say 230 volt AC if we really need.
That's good. So in our Anacon turbines, we have the transformer in the base. Our remote switching unit is one level up, divided by a floor plate. We have to carry out a fault ride through test, which consists of running the turbine at reduced power, approximately 200 kilowatt, and switching off switchgear and then back on again while in the base. Would you say that this is a dangerous procedure? Do you want me to read that again? Or can you read it from the screen there? Can you see the chat there, can you?
Yeah, I'm reading it from the screen.
Yep.
It would depend on, obviously, arc flash is very influenced by the distance that you are from the exposed conductors. So saying one level up, it's difficult to determine whether that's kind of 2 meters, 3 meters. The distance obviously makes a big difference to the arc flash. I would probably be more concerned about actually the fact that the generator's on while you're doing this, because a lot of our calculations within turbines are based on the generator not being on while people are in the turbine. But it would require an individual assessment. It's not easy to say yes or no at this point. If you can do it in an alternate method, would probably be better. As I say, if you can remotely switch that by some other method, then obviously it would be a better position.
Yeah.
Well, what I can add to it, it depends how you do the test, if you keep opening things or it just operates normally.
Mm-hmm.
If it operates normally, officially you don't really need PPE, unless it's like 80 calories or something and your overall risk is very high.
Yeah.
But for normal operation, that's what NFPA said. If for normal operating conditions, the likelihood is very low.
Yeah, that's good. Good to point that out. Thank you for that. Should both members of switching team wear full RFAS PPE, including balaclava and helmet?
If they stand in the access boundary, yes.
Yeah, that's what I was going to say. Yeah.
And also, it would depend again as well. If it's in its normal operating condition, if panels are closed, etc., you've got to take those into consideration as part and parcel of your
There's also the fact that
switch operations.
the principle is that I assume that second person is there for safety if something happens to the first person. So in that case, they may actually have to go into the zone to pull that person out or some such. So therefore, it would be logical for them to actually still wear the PPE, because then they can enter the zone without putting themselves at additional risk.
Yep.
Yeah.
You really don't want 2 people in the zone if you can possibly help it, do you? Furthermore, just believe it or not, coming from a PPE organization, it is your very last line of defense. And so we've just spoken about chicken switch, umbilicals, is that every avenue that can be explored to remove people from the risk, that's what should happen.
Yep, that's good. Okay, we've got an interesting point here. So we wrote guidance document at Renewable UK on switchgear covering LV and HV. So thank you for that, Chris Streetfield. Appreciate your input there. So thanks to the update, Ali. So it's for the wind industry we're talking about there. And so it's not off there. So LV control compartment of switchgear just above VCB ACB requires a separate R flash label. Can you see that there? Can you?
I know that's the reference to the slide, I think, with the forms of separation that they show.
Yes.
And what technically you could put the label just for clarity, but once you start to do this, then you have to put labels everywhere.
Yeah.
And that's the generally question if you are happy with it or not. Normally speaking, if the panel is like this and you don't have any other panels like this in the system, it would be better to actually put the label, because what I saw that you can have a supply from top down, and I opened something which I think is control compartment, which are bus bars. So technically speaking, would be better actually to label it as a, let's say, control compartment. I would say this way, not even that is below 1.2, because technically speaking, if there would be accident, like you have a rat on the bus bars, unlucky rat, and something explodes now, the fact that you are standing in front of this control compartment doesn't help you anymore. You are still in the same place, you know. And but from overall risk point of view, it would be good to know that the compartment you are opening is a control compartment. That's the only, I would say, the labeling that you require. It's not the arc flash label.
That's good. Can Jenny advise how to evaluate the risks from venting switchgear, flash and blast in enclosed areas such as wind turbine towers?
This is quite a difficult one in terms of again, this is normally done by the manufacturer, gives a lot of the advice on this. One of the main things is, if possible, to ensure that the venting is not to an occupied room, obviously, because you don't want to save one person in one room and put a person in another room in increased hazard. So it's partly looking at where the venting goes to. Obviously, if you can have fully arc resistant switchgear that doesn't require venting, then that's a preference in that kind of situation. But yeah, venting upwards towards the ladder is obviously a bad idea, which I have seen in some designs and we have questioned. But it is very much an individual case. But yeah, it's a very valid point that does need consideration.
That's really good. Thank you, Jenny. So different SAPs have different viewpoints on viability on using arc flash PPE. Some states it's not required, legal. Is there a UK legislation on arc flash?
So I think you know better, but the recent fine for atomic weapon establishment, £660,000. I think it says that, yeah, it is.
Yeah.
And that was near miss, I think, only.
Correct. Yeah, it was.
I would, yeah, generally it is. There are some legislation behind it that you have. I don't remember now the name because it's a long one, but it is.
There's a lot of legislation. I will put into the chat now. I will paste into the chat all the UK legislation relevant to it, covering a whole wide range of varying industries, because there are different pieces of regulation for different industries.
Good.
And I think as well, when you're considering things like as low as reasonably practicable, then arc flash PPE is practicable. So therefore, it's not an excessive amount of additional cost to use arc flash PPE.
Yeah, that's good. Thank you for that. So last one now. I think I have to wrap up for this. So in case of arc flash case, PPE should be used in limited approach boundary or in restricted approach boundary.
So there are two things behind it. The limited and restricted is a shock hazard protection boundaries, not arc flash. So they are combined in an FPA, but those are separate things. They are fixed and they are depending on the voltage level that you are working with. So of course, in restricted approach boundary, if you whatever do, you need PPE just because of the protection for the shock hazard. And there is also something we call a little bit different in Europe than from US. And of course, if your arc flash boundary is bigger than limited approach boundary and you are doing something with it, then yeah, you have to have your PPE. So just because you approach limited approach boundary and you didn't do anything yet, or you work with it, then you need to have your certain amount of PPE that you generally need as an electrician in this case.
Yeah, that's good. So in case of arc flash case, PPEs should be used. Sorry, it's the same question I believe again. We're much to answer now. So
I think we should be drawing to a close soon, Anthony.
Yeah, that's it. No, that's it. We're through with the questions now. That's the last one. So
excellent. Well, everyone, really appreciate the time for you being on. As I said, the recordings will be circulated with a slide deck. Marcin's details will be circulated for anyone who's got any further detailed questions to ask. I think in summary, really, so we've given us some excellent tips today of how you can remove people from the hazard, how you can eliminate the risk. PPE is your very last line of defense. I also think it's very clear from today's session that there is a myth that HV is where the risk is. in that LV is where the risk is, and it's an area that we need to be aware of and understand that. I also think that these mitigation techniques, we've spoken about art-fast mitigation systems, you know, there is a primary purpose as far as saving lives and removing people from the risk, but also the benefit it has to your own infrastructure. So if you can avoid ripping apart 2 or 3 switchboards or panels, then that also has a positive implication within your business from a electrical infrastructure perspective. So I think with that, we're pretty much ready to wrap up. Really appreciate each and every one of you attended. I trust you found it insightful. Please give the feedback on the Q&A, and we'll join in a virtual round of applause for Marcin and Jenny joining us and sharing with us their intelligence, experiences, and practical advice. It's been excellent. Thank you very much.
My pleasure. Thank you very much.
Thank you.
So thank you very much all. Marcin and Jenny, if you can just stop on for a few moments, and the rest of you, have a good morning, afternoon, or evening. Enjoy your breakfast or sleep well. So I'll just wait for those to leave and we can but I think we could probably close this down, and I'll just quickly send a quick Teams invite, Marcin, and to Jenny, if that's okay.
Yep.
Yep, sure.
Thank you.